Okay, we're going to do 3 problems on the center of gravity inquiry. Part 1, um, there's a meter stick. And if we wanted to balance this meter stick, you would obviously put a balancing point or a fulcrum right underneath the 50. But we're going to do something interesting. We're going to move the fulcrum over here, little balancing point on this. And of course, this thing would not balance, right? It would crash down over here on this side. We're going to put it at this right here is the 35 centimeter mark, this being the 0 over here and the 100 over here. Okay, so we're going to put the 35 centimeter mark, and clearly this thing's not going to balance. But what we can do is we can slide a weight out here on this edge and get it into a place where it would actually keep this thing balanced. Even though this is a lot bigger part over here, it would actually be balanced on this thing. And so we're going to come out here, and at the 10 centimeter mark, we're going to put, there's a clip, and then on that clip is a mass that's hung on it. The mass, it says, is 34.7. Remember from the last problem that all the clips were 21 grams. So 34.7 plus 21. So this is actually 55.7 grams there. Now, the point of this problem is, what is the mass of the meter stick? We're trying to find the mass of the meter stick. Well, the mass of the meter stick would go where? Well, it's a uniform meter stick. It's the mass is evenly distributed within the meter stick, the actual wood part of it. And so whenever you have a uniform mass, the mass of the object goes right in the exact center. Well, the exact center of a meter stick is like right here at a 50 centimeter mark. And so right here should be the mass of the stick. And so I need to figure out what that is. And so you could do ups and downs here. Well, actually, you can't do ups and downs. I mean, you could start doing a table, but I'll show you why it's worthless. Down would be 55.7, and also the mass of the meter stick. What's the up? Well, the up would have to be equal to both of those. And since I don't know the mass, I can't add them up and get an actual number. The mass, or the up force, would be right here where it's supporting, obviously. And we don't know what that is because it's 55.7 plus m. So we'd have, an unknown here, and we have an unknown here. Now, I don't care about this unknown at all because that's not even what I'm asking for. So I'm going to use that as my reference point. There's going to be my reference point, and I'm not going to worry about ups and downs. I'm just going to worry about torques. I'm going to balance the torques around this reference point. So over here, we have a distance over and a force down, and that would be a counterclockwise torque. And that's 10 to 35. That's going to be, I'll just do it in decimeters. That would be 2.5 over. So 2.5 times 55.7, that should equal this distance over here, which would be 1.5, 35, and then 40, and then 50. So that'd be 1.5, or you could do 15 over if you wanted. 1.5 times m. And that's all I really need. It's a pretty easy problem. 2.5 times 55.7 divided by 1.5 equals, and the meter stick is 92.8 grams. That's the mass of the meter stick. By the way, I'll just point out that, normally we call these forces, parallel forces, but these aren't really forces, they're masses. And if you wanted to, you could convert them both to kilograms, or you could convert this to kilograms and then multiply by 9.81 to put it into a force. Then solve for this, but then you're going to get a force over here, and I wanted the mass in meter in grams. So you get a force, you could then divide by 9.81 and then turn it into grams. But see, that's you already did that all the way over here, so it's a waste of time. So this isn't really physics equations, it's balancing stuff. So you can leave these distances up here, don't need to be in meters, they can be in decimeters or centimeters, whatever, as long as they're in the same. And on the other, the forces, they could be in newtons, but they could also be in kilograms or grams or whatever. It doesn't matter. You can leave it all at the same. So hopefully that makes sense for that. Okay, for part 2, we have this big meter stick again. And I'm going to do 1, 2, 3, 4, 5, 6, 7, 8, 9. Sorry, they're not totally even, but it's going to be good enough. And on the 10 and 20 right here is where our fulcrum is going to be balancing on it. So again, we have clips for these masses. So right here, instead of 500, it's a 521. And right here, this is not on the end, it's at the 1 centimeter mark. So I'm gonna write that in there real quick. Right here, we have a 1,000-gram mass, and it's on a 21-gram clip too, so it's 1,021. And then right here, we have a 121. And then right here, we have a 221. And then again, we can't forget that in the middle of the meter stick, 10, 20, 30, 40, 50, right here, we have the mass of the meter stick. The mass of the meter stick still needs to be here, and that's 92.8 grams, like we just figured out. So the key on this one is that if you came in and saw this station set up, this is actually not balanced. It looks like it is balanced right now, but this end of the meter stick would actually be down here on the ground. This would be sticking up like this. This stuff over here is heavier than all this stuff over here. So what we're asking is, where do I put a 100-gram mass and its clip? So 121-gram mass, where do I hang this to make this all balanced? And this is not that bad. We can just, again, measure from right here. We don't actually ever have to know what this up force is. We'll just measure from there and we'll balance the torques all the way around it. So over here on this side, we have counterclockwise torques. These two things are going to counterclockwise torques. So I'll do these in decimeters again. So one decimeter times 521 plus 1.9 times 1,021, 1.9 because this is 1, and then remember it was almost all the way over, so 1.9. Okay, that will equal all my torques over here, which would be clockwise torques. So I have 2 times 121 plus 3 times 92.8 plus 5 times 221. Okay, and I shouldn't put equals right now. I should just make a chart, really, is what I should do. These are clockwise and these are counterclockwise torques. And let's go ahead and see what they are. So 521 plus 1.9 times 1,021. This over here is 2461, we'll call it. And then over here, I got 2 times 121 plus 3 times 92.8 plus 5 times 221, and I get 1625.4, and clearly we need some more over here. So I'm going to take this and subtract this to see how much more we need. And we need 835.6. I need 835.6 more clockwise torque. So I know the force is going to be 121 grams, or the mass is going to be 120 grams. So this amount of torque should equal 121 times X, and we'll figure out how far over from this reference point should it be. So I'm going to divide that by 121, and it says 6.9. So 1, 2, 3, 4, 5, 6.9 right in here. This is the 90 centimeter mark, so 6.9 over would be the 89 centimeter mark is where you want to hang this 121. I'm going to put that 121 right there, and that'll actually balance the whole thing. Okay, part 3 is a lot easier. There's a board here. It's not a meter stick. It's just some big board, and it's actually 20 meters long. Okay, it's being held up this way with a force of 800, and over on this end, it's being held up with a force of 600. Now, what that tells you is that this board does not have uniform mass. It does not have uniform mass because the left half of the board is heavier than the right half. Okay, so we can do ups and downs, and you'll see we have a total up of 1,400, and that means we need a total down of 1,400, which tells you what the weight of the meters, not the meter stick, the weight of the board is. The weight of the board is 1,400, whatever, yeah, it's newtons, I guess, 1,400 newtons. The key is, and this one is where do you put the center of gravity? Okay, and I can measure from either side. I'm gonna go ahead and measure from this side over here, so I don't have to worry about the 800. So somewhere out here, I'm gonna put a 1,400, and I actually know that it's closer to this end because that 800 is bigger than 600. So somewhere in here, it's gonna be the 1400, okay? And I want to figure out how far over that is. So I'm trying to find x. So I can take x times 1400, and that would be a clockwise, 1400x. And then counterclockwise would be all the way over 20 times 600. That'd be going around the other way. So that's 20 times 600. And that's all I need. So 20 times 600 equals, divided by 1400 equals, and x right here is 8.6 meters. So the weight of this stick, or the center of gravity of this stick, is 8.6 meters from the left end. And that's all you really had to do for that problem.